Started now.
Okay, cool. Hi everyone. Welcome back. Glad to see so many people coming back to the lectures. Uh, let's just quickly recall where we ended the last lecture. We were in the middle of a proof of a construction for the Ramsey number R of 3, comma T. Hey. Right, so we wanted to give a second construction showing that the Ramsey number R of 3 comma T is at least something like T to the 3 half, right? That's where we were at the end of the last lecture. And let's quickly recall what the construction was. And it came from a generalized quadrangle, the only infinite family of generalized quadrangles that we saw in the lectures. But finally, we took a subgraph of it, and then we noticed that the graph is in fact a Cayley graph. So Q was a power of 2, so an even prime power. And our graph was a Cayley graph for this group. This is just the vector space addition group with respect to a generating set S that was defined as follows. We had ax squared, and a comma x were non-zero elements of the field. And for those of you who don't know what Cayley graphs are, this is the definition here. We have two vectors of the group, two elements of the group adjacent to each other in the graph if their difference is in the set S. Okay, so this is the definition of our graph. And what we wanted to show was that if you have an eigenvalue of this graph, which is not the largest eigenvalue, so the eigenvalue corresponding to the size of S, so Q minus 1 square is the size of size of S, the generating set. This is the degree of the graph, the regularity of the graph. So if you take any other eigenvalue, then we wanted to show that it is bounded from above by a linear function in Q. In fact, 3 times Q here. Okay, this, if you notice, is roughly square root of the degree, right? That's what we want to show. And now I gave you a reference last time. I can give another one in the chat. This one, where you can see that whenever you have a Cayley graph of an abelian group, you can write down all of its eigenvalues via a really nice looking formula. And this was the formula that we had. So you just have to trust me for now that this works. I won't be proving it, but it's not super complicated to actually prove this. Because it's easy to just plug in these things and check that these are eigenvalues, and then you can do some sort of a dimension argument to say that they must be all of the eigenvalues of the graph. Okay, so the eigenvalues of this graph G look like this. So for every vector U, so every element of the group, there is an eigenvalue corresponding to it, which is given by this sum. So the sum is over all elements of S minus 1, which is this, minus 1 raised to the power trace of U dot V. This is the standard dot product. You just take coordinate-wise multiplication. That's all it is. And now notice that this element, this U dot V, is inside FQ, right? And the trace then is inside F2. So the trace is either 0 or 1. Okay, so this is minus 1 to the 0 or minus 1 to the 1. That's what this is. And if you don't know what trace is, then trace is just the function. This is the absolute trace from this larger field to its prime subfield. We have this function, which is an F2 linear function given as follows. All right, so this is where we were. And we want to show that if you take any other eigenvalue except for the largest one, and what are the largest ones in this formula? Well, if you take the 0 vector here, then all of these things are 0. And so the sum, if you just take the sum, it's the cardinality of S. So that's the largest eigenvalue. So if you take any non-zero vector U, so this is where we are, start with any non-zero vector, and we want to show that this eigenvalue given by the formula has absolute value linear in Q. That's what we want to show. Okay, so let's proceed with that. I have written it out in an expanded form. So if you just take the dot product, then note that the element here is a comma ax squared. If your vector u is u1, u2, u3, take the dot product, you get something like this. All right. Now, to simplify the sum a bit, let's just do this substitution. Let y equal to a over x. And let's define this polynomial, which is u1 times x plus u2 times x squared plus u3 times x cubed. Then you can write this eigenvalue as the sum of a is an fq star, y is in a set t. I'll let you know what the set t is. And you have minus 1 raised to the power trace of y times f of x. Okay, and where T is just the set of trace 1 elements. So it's just all those elements of the field for which the trace of Z is 1. And if you see the review sheet at the beginning of this course, you'll realize that this thing is, the cardinality of this set is just Q divided by 2. Okay, so this is the sum that we want to evaluate. And in fact, we want to just, at some point, we'll take absolute values on both sides and show that the absolute value is at most some linear function in Q. To make this simpler, what I will show is that for many choices of, let's say, there is not, yeah, this should be an X. Sorry. This should be an X, right? Yeah. Okay. So what I will show is that for many choices of X, the sum inside is in fact 0. So many of these terms vanish and the remaining terms are not that many, so you can just approximate them sort of trivially. So what I claim is that if f of x is not in your binary field, so if it's outside it in the larger field, then this sum of y in t trace of, minus 1 to the power trace of y f of x is 0. So this is really, this will be a lot of terms. And for all the remaining terms, we don't really say anything, but that this will suffice once we show this. So let's state this separately as a lemma. And this is in fact a nice exercise in finite fields. So if you take any element beta outside this subfield and you have this sum where you have the trace of y times beta, beta is f of x, and that we saw before, then the claim is that this is 0. And the proof is sort of a standard trick if you have seen character sums or these sort of sums in finite fields. So you have this sum sigma, you multiply it by something, we'll see what it is, and then you show that multiplication doesn't change sigma. So it's the same sum. But if this thing you multiplied with here, it will turn out to be, yeah, I'll just write like this. This will turn out to be minus 1. So minus 1 times sigma will be equal to sigma. So sigma will be 0. Yeah. We don't have, yeah, this is like a sum of numbers. Yeah, it's not, yeah. These are real numbers. It's not an element of F2. So I was confused for a second that 2 sigma is 0. Okay, anyway. Yeah, so what are we going to multiply it with is you pick an element T of your field, which has trace 0, such that the trace of T times beta is 1. And I leave it to you. F of A is in the exponent then. Wait, so there's a remark by some, maybe this was from before. Yeah. Oh, yeah, I already changed it. Yeah, okay. Yeah, sorry, I didn't see the chat. Yeah. Okay, so I claim that there exists such a special T for which the trace is 0, but the trace of T times beta is not 0, it's actually 1. And this I leave it to you to show that this such a T exists. And in fact, this only exists if beta is not in the subfield. And if this is there, then when you multiply by minus 1 raised to the power trace of T times beta, and of course, this thing is 1, so this whole thing is just minus 1, And if you multiply it and you take these terms inside, then because trace is linear, yeah, no, trace is linear. Yeah, trace of a plus b is trace of a plus trace of b, I believe. Yes, yeah, and then the trace of t is 0. So if you just plug this in here, you'll realize it doesn't change the sum. Okay. So if you are convinced by that, then finally, as a corollary, we have the lambda. Let's just write it down nicely here. I think we'll need some space. Is equal to the sum of all the x which are in f inverse of f2. So f of x should not be in f2, and you subtract the 0 element here, right? Because x was non-zero, but this wouldn't matter too much. And then you have y is in t minus 1 to the power something. Now, if you just take the absolute value and you observe that how many terms are there in the outer sum. So remember that f of x equal to c for any constant c is a non-zero, non-trivial polynomial equation of degree at most 3, right? Our f of x was this. So if f of x equal to a, if you just plug in some a, then the number of solutions is in fact at most 3, right? A degree 3 equation has at most 3 solutions. So if it was 0, if f of x was 0, that has 3 solutions, f of x equal to 1 also has at most 3 solutions. So there are at most these 6 terms outside. So in fact, the following is true, is less than equal to 6 times this sum, minus 1 to the power whatever something and more. And now you just take the triangle inequality. This is less than equal to, each of these terms has absolute value 1. So this is less than equal to 6 times the cardinality of t, which is 3 times q. Okay, so just playing around with some these character sums, basically, if you know what those are. Okay, any questions about this? I left out one claim that is actually a nice exercise, yeah, to prove that such a t exists. That's where we use that beta is not in the field. Okay, yeah, if there are no questions, let's summarize what we did. Okay, so we started with a generalized quadrangle of order q minus 1, comma q plus 1. So it had these many vertices. And we actually took a sub. Can you please explain where the 6 came from? Yes, okay, sorry. Yeah. So I said here that f of x equal to c for any constant c is a degree 3 equation, is a non-trivial degree 3, or well, up to degree 3. It could be degree 1 or 2 as well, degree at most 3 equation. So there are at most 3 solutions for, let's say, f of x equal to 0. And then there are at most 3 solutions for which f of x is 1, right? That's where you get this 6. Okay, we are summing over all x for which f of x is in f2. Yeah. Okay, so let's summarize. And this will be important because that's where I give you some new research ideas on how to actually improve some of these things. We saw that we started with a generalized quadrangle of order q minus 1 comma q plus 1. It could be q comma q as well. It should be fine, as in we care about asymptotics. So n was q cubed. And because of this eigenvalue being linear, you apply the expander mixing lemma, or you apply the Delsart-Hoffman bound, or in fact, you can just apply a direct counting argument on the original graph, but not on this graph. But anyway, using the eigenvalues, we showed that the independence number is around q squared, is at most q squared. Okay, yeah, this is roughly. Like it could be some constant times q squared. This could be some constant times q cubed. I'm not being precise. Okay, so think of them as theta of q squared, theta of q cubed. And then using this graph, because it's a triangle-free graph with independence number only q squared, we get a lower bound on r of s comma t, r of 3 comma t, sorry. We get a lower bound of the following form. I should say. Okay, so we get an explicit construction showing that r of 3 comma t is greater than t to the 3 half multiplied by some constants, doesn't matter. All right. Now, what happens if we start with some other generalized quadrangle? So let's say we start with a generalized quadrangle of order q comma q squared. They also exist. Then the number of vertices is in fact, the number of points is in fact q to the 4. And you can show that the independence number is about q cubed. So say there was some magical process which was analogous to what we did with this generalized quadrangle, right? It was not such an obvious thing. We had to destroy all these triangles by going to each line and making them basically bipartite. So if we could potentially do it with such a generalized quadrangle, then if we can do it, then we will get a lower bound of the form t to the 4/3, which is actually worse, right? 4/3 is, yeah, it's worse. So it looks bad. But then you make the observation that what if we started with a generalized quadrangle of this order? Then we will have q to the 5 vertices. And interestingly, the independence number, if you do the calculation, turns out to be of size q cubed in the original generalized quadrangle. So if there was such a process and the independence number doesn't change too much and you make the graph triangle free, then you will get an explicit construction of the following form. And this will break the current best result. So this will be a pretty good breakthrough result if you can actually do it. Right? So this is a strategy. Just understand what the generalized quadrangles of this order look like, try to really understand their structure, do something clever with them, destroy the triangles, and make sure that the independence number does not increase by too much. And then you have an explicit construction, which is better. Maybe you can start with another family. There are generalized quadrangles of order q cubed comma q squared, and I'll let you figure out what the bounds are, but this will also improve the current best bound. Okay. So start with your favorite GQ family, which of course, if you don't know what GQs are, yeah. Okay, a question from Emilio. Yeah.
It's just a quick question. Have all of the known examples of GQs been sort of manipulated to form graphs like this? Have they all been?
No, only this one. That's what I'm trying to tell you.
Oh,
only
sorry.
this one. So if you can do the manipulation for any of these GQs, you'll have a new result in Ramsey theory.
Cool. Okay.
Yeah. Right. So that's a very promising approach, of course. So we tried it, me, Valentina, and John Bamberg. I think Valentina is here. Yes, Valentina. And so we tried this with this GQ and we got stuck. We tried many different ways of sort of coming up with analogous KD graphs and doing the same sort of a thing. Things end up getting a bit hard because if you, you start getting non-abelian groups and their character sums and their eigenvalues. So things get out of hand pretty quickly. So, but if, it's definitely worth trying, like trying really hard for this one and also for this one. And either one of them would improve the best known bound for explicit constructions. Okay, these are explicit constructions. Yeah.
And just off the top of your head, what are the more common names for these? I can look it up in a paper, but do you remember what?
So this one, this one is like a Hermitian generalized quadrangle, maybe a dual Hermitian, the known families. So yeah, maybe a dual one. Yeah, someone in the chat can correct me, of course. There are many finite geometries. So, but Hermitian generalized quadrangles, that's one thing. And these are, I think, yeah, both. This can be seen as a Hermitian or also a dual elliptic quadric. Yeah. But if you just look at all the classification of generalized the known examples, you'll see these parameters there. So do this process with any one of them, look at their group theoretic models if you want, and maybe you'll get something. Okay, so exciting stuff. Of course, I was very excited, but so far we haven't been able to do it, but maybe someone else can. And maybe we can after a while if we get some new ideas. Okay, any other questions before we move on? This is all I want to say about the explicit construction. Yeah. Someone has a
Where
question?
are the independence number bounds coming from here? Are they also from just estimating the eigenvalues?
So for the generalized quadrangles, it's a strongly regular graph. So you have the eigenvalues. You can use that if you want, but there's a direct counting proof as well. You don't actually need the eigenvalues. So the independence number I've written down here are those of the generalized quadrangle, right? I hope that's clear. You have to still do something, manipulate them, and still hope that they don't change too much. That's the idea.
Great, thank you.
Yeah, so the counting argument I can quickly sketch. If you have an independent set, let's say I, then through every point of this independent set, there are these t+1 lines. If you have a GQ of order s comma t, there are these t+1 lines. So you can count the point line incidences where the point is in the independent set and you have a line through them. So this is one way of counting them, multiplied by t+1. And the other way is the set of all lines, but every line intersects an independent set in at most one point. Right? So this thing is less than equal to the cardinality of the line set. So that's how you can also get the independence number.
So
and I think
saying that the
yeah. Sorry.
You're saying that the eigenvalue gives the same bound?
Yes, yeah.
Oh, okay.
Yeah, so the eigenvalue of the strongly regular graph of the generalized quadrangle, they give you the, exactly the same thing. You can check that with the parameters I have in the notes. Just plug them in, you'll get exactly the same thing. And it's actually tight in many cases. But in many cases, it's also not tight, just that I don't know if it's very far from the truth, asymptotically for our purposes. For finite geometers, yeah, they usually stop at, oh yeah, it's not tight, that's it. But then extremal combinatorics, people will ask, oh, how close to the truth it really is, right? Asymptotically. And that I think is open in many cases. But these are very nice examples to work with, to understand this finite geometry of them and just, have a go at it and try something there. Any other questions before we move on to the next section? Oh. Okay, cool. So that's it about the explicit constructions. But now what's really beautiful about this explicit construction that we had of an ND lambda graph with these parameters. So we had this graph, which was by Kopparty, the graph that we were just studying, is that you can use this graph to actually give a better bound on the Ramsey number. So instead of this bound, you can actually improve this, but then the construction is not explicit anymore. So you start with this explicit graph, and you can create some random subgraph of it to actually give essentially tight lower bounds on the Ramsey numbers. So that's pretty cool. Okay. And this follows from this very nice observation, which was observed in many papers, I think. And Yuval here can actually tell us more about the history of it, because I learned about it from him. And I saw the lemma stated in this in his notes, which maybe he can link to in the chat as well. He has some really nice notes on this topic. And here's a very, very general result, which says the following. Okay, so start with any KS-free graph. Nothing about its eigenvalues, whatever, just start with any KS-free graph, your favorite KS-free graph on n vertices, such that the number of independent sets of size t in this graph is not too much. So it's bounded from above by m to the t, m to the power of t, where m is some number smaller than n. Then the Ramsey number R of s comma t is strictly bigger than n divided by m. Very simple looking, like a really beautiful lemma. Yes, the notes are, exactly. Thank you. Yeah. Okay, so this is a very, very nice lemma that you should all keep in mind. So for any KS-free, or in fact, we'll see that This could be any F-free graph. If you can bound the total number of independent sets of a certain size in a non-trivial way, because a trivial bound for sets of size t is just n choose t, right? Which is like n to the power of t. So that's a trivial bound. If you can give any non-trivial bound, then you get something nice. You could potentially get something nice for the Ramsey numbers. And it also has a very simple proof. So I could just say one line and that would be enough, but I'll actually do it in detail. So the proof, as some of you might guess, is take a random subset of size n over m. So on this graph, which has n vertices, just pick n over m vertices uniformly at random. And I claim that with a positive probability, this induced subgraph will not have any independent sets of size t. So note that because it's an induced subgraph, this will also be ks-free. So we will have a ks-free graph with no independent sets of size t on this size, and that gives you the lower bound. Okay, and here is the proof. So let I be an independent set of size t in your original graph. Then what's the probability that I stays independent? So the probability that I is also independent in the subgraph is simply the probability that this set of t elements is in your choice of n over m elements. So this is in fact exactly equal to n over m, n minus t, choose n over m minus t divided by all possible divided by n, choose n over m. Okay, this is the probability, just exactly equal to this. And then you can simplify this. You can have n minus t factorial and then divided by n over m minus t factorial. Then you have this n minus n over m factorial that cancels out. So you have n over m factorial divided by n factorial. And this is equal to, if I'm not wrong, n over m multiplied by n over m minus 1 minus t plus 1. Right? I hope it's correct. I think it is. Divided by n times n minus 1 dot 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 n minus t plus 1. Yeah. And now this term is equal to 1 over m. And if you just check all of the other terms, they are strictly less than 1 over m. So this thing is strictly less than the following. And now that's it. If you know what the union bound is, because this is the total number of independent sets of size t. This is the upper bound on the total number of independent sets of size t. So if you go over all independent sets of size t and take the probability that any one of them survives, then this probability is strictly less than 1. So the probability that all of them are destroyed is positive. And that's the proof. Okay. Any questions? No? Very simple looking lemma. Let's see how to use it. And the way we will use it is show a very general result for ND lambda graphs. So remember, these were the pseudo-random graphs we were talking about. We will show that these ND lambda graphs have such a non-trivial upper bound on the number of independent sets of size t if t is large enough. So if t is larger than this, some function here, then the number of independent sets of size t is at most something here. That's what we will show. And then once you have this, just use your favorite ND lambda graph, which is free of some clique or some other graph, and you get a nice lower bound on Ramsey numbers. And yeah, I should say that this whole thing, this whole idea is by Mubai and what started. There's a reference. So in my on the web page of the course, I have added a section on references. So you'll see the paper there where they talk about this. Okay, so let's just go through what this lemma is. We will prove it later on if we have time, but for now we want to understand what this is. Okay, so it says that if you take t to be larger than 2n log square n divided by d here, then the number of independent sets is bounded from above by this thing. So this is the main thing you should keep in mind. Lambda divided by log square n to the power t. This is just a constant. It won't matter too much. And why is this sort of non-trivial? Well, you can convince yourself, and this is also a nice exercise, that if t was only slightly smaller than this, so if this log square factor was not there, so if t was just slightly smaller, if t was n over 2d roughly, then there are at least d to the t independent sets. And this is just counting, just greedily choose your independent set, and you have some expression, you can see that that expression is at least d to the power of t. And now observe that if your lambda, this in the ND lambda graph, this eigenvalue, if this was smaller than d, if this was some little o of d, and in case of optimal pseudorandom, if lambda is like square root of d, then we really have a big improvement, right? So up to this point, you have some function like this, and suddenly when you just go a bit higher than that, then you have a much smaller function. So the growth is much, much smaller. That's what's cool about ND lambda pseudorandom graphs, among many other things, but this is really nice. Okay. And as a corollary, we just get that if, wait, let me erase this. So as a corollary, if G is F free, or for now, we are sticking to KS free. If G also happens to be KS free, which it was in the case of the previous construction we saw, we had here an ND lambda graph, which was triangle free, K3 free. So if it was KS free, then the Ramsey number R of S comma T, where T is larger than this thing over here, is strictly greater than, you can just divide n by that. So you get n divided by 4e lambda log square n. Okay, we're just taking n divided by m. This is m, this thing inside the exponent. Let's see what it tells you in the case of the only K3 free ND lambda graph we saw. And in that case, we have these values. N is q cubed, d is around this thing, which I hope is correct. Maybe it's not. Yeah, it is correct, I think. Something like this. It's basically q squared. I hope this is exactly correct, but if not, don't worry. D is like q squared, n is q cubed, and lambda is the square root of d. It behaves like the square root of d, so it's q. And in this case, let's just compute these things. We have t is equal to 2n log square n divided by, it was d. So this is something like q log q. My logs are always with base 2, just letting you know. Won't matter now, but still. And then your lower bound on r of s comma t. So wait, on r of s comma q log q squared is n log square n by lambda, so something like q squared log q squared. If you want to write this as a function of this, then what you get is r of s comma t is greater than t to the 3/2. Sorry, not 3/2, t squared. You just take the square and divide it by log t squared. Here S is 3. Yes, here S is 3. So we have K3 free graph. Yeah. We have proved a bound which is really close to the truth. It's just a log t factor away from the truth, if you remember what the value of r of s comma t was. That's pretty cool that you saw a proof of that, which is very different from the original proof using purely probabilistic ideas. Okay, and this leads to some exciting ideas, which is what Mubai and Vastrati's paper was about. It says, now let's do this for s larger than 3, right? So say we have some s greater than or equal to 3, and we have, say we somehow construct a ks-free graph, which is nd lambda, and the d over n. So here d divided by n was something like q, which was n to the minus 1 over 3. So it's say n to the minus 1 over some f of s. And lambda is square root of d, so it's optimally pseudo-random. If you can construct or show the existence of any such graph for any given s, then you get the lower bound, this lower bound on r of s comma t. Okay, so recall for s equal to 3, we know such a construction with f of s equal to 3. So we know this. What about s greater than or equal to 4? Well, that's where it gets really hard. And what we would ideally want to show is a construction. We want to show construction or even existence. Yeah, construction as an explicit or non-explicit doesn't matter. Some construction where f of s is equal to 2s minus 3. Because if you plug in 2s minus 3 over there, you get a lower bound of the form t to the s minus 1 divided by t to the by log t to the power 2s minus 4. And this is really the upper bound as well on the Ramsey number. So the off-diagonal Ramsey numbers would then be, so this would imply, if you can show something like this, then this would imply that the Ramsey number r of s comma t is equal to some constant cs times t to the s minus 1 and some little of 1 term here, the log t factors. So if you can give a construction which is really this good, then you have solved the one of the biggest open problems in combinatorics, let's say, right? That's what's really cool about the work of Mubai and Verstraeten, who made this very simple observation. When you look at the proofs, they're really, really simple, but somehow no one observed this before. So this is really cool. And this actually gives us some hope that these Ramsey number bounds, the bounds on these Ramsey numbers can actually be improved. And what's the best construction that we know? Well, sadly, the best construction that we know is of size f of s equal to minus 1, and that's by myself and Ferdinand and Valentina Pepe, who's there in the audience. So the best construction that we know has f of s equal to s minus 1, the best general construction for large s, which improves the earlier best construction of Noga Alon and Mikhail Krivelevich that had s minus 2. This was Alon and Krivelevich in 1990 something, 6, 7 maybe, and this was 2020. And the only reason why we were actually able to improve this was because we used a lot of finite geometry, our knowledge of different sorts of finite geometries, and we applied that to this problem, and we just we improved this basically. And it was not too hard, and we actually thought this would be like a minor sort of a result, and we'll be able to actually prove this thing. At least for a while we thought this will be doable, but it turned out to be too hard. So I don't know. We'll hopefully keep working on this and get something else also. But this is what we have so far. And sadly, the Ramsey bound that you get from this construction is actually slightly worse than the purely probabilistic bound for large S. For S equal to 3, it's fine. There's a different construction, but our general construction does not match the best known bound for Ramsey numbers right now. But if you can improve this, to even some S plus epsilon for any positive epsilon, you will break the current best bounds on Ramsey numbers. So this is, in my opinion, the most promising approach towards improving the lower bounds on off-diagonal Ramsey numbers. Any questions on this? Yeah. Any questions, any remarks? So we will soon proceed towards actually giving you this construction. And before doing that, we'll actually build more theory from finite geometry, in particular the theory of polar spaces, which is really nice in itself, but our aim is to potentially use that to improve our construction as well. So I'll give you my construction, and then hopefully we will be able to improve it in some time. I don't know, in a few years, maybe. We'll see. And that's the plan. But now that I have a couple of minutes, oh wait, let me just summarize. Yeah, I just summarized this again. I don't know why I wrote this there. So yeah, this is what we want. N to the 1 minus 2s minus 3, and then this will give you the bound. Now, I don't think I have enough time to actually prove the lemma, because I wanted to finish this before the break, but let me quickly sketch the lemma that was here, the proof of the lemma. So this lemma over here. So if G is an ND lambda graph, we want to bound the number of independent sets. Yeah, just say a few words about it. So we're just going to count the number of ways of actually picking such T elements. That's the basic idea. So say we have picked some elements, Vk are independent. We let all possible choices of vertices such that V is not adjacent to any Vk. And so say this is my set Sk. This will be the all possible choices at the kth step. Say you want to pick, or the k plus 1 step. And here you define a subset of this, Tk, which is defined as follows. Tk is the set of all potential vertices which don't have too many neighbors. So the number of neighbors of V in Sk is at most d over 2n times the cardinality of Sk, if I'm not wrong. So something which doesn't have too many neighbors in Sk, right? And then the main thing, the way this count works, and the details are in the lecture notes, so you'll see all the details here, but the main idea is that if you picked any element outside Tk, then it will have a lot of neighbors in Sk, right? It's the complement. And if you pick that, then the number of choices you have at the next step reduces by a lot. So the cardinality of Sk plus 1, in fact, you can show it becomes like something of the form, yeah, d over n or something. Yeah, I don't remember, but something like, maybe it's somewhere quickly. It becomes, yeah, d over 2n times Sk. If you picked something, yeah, oh, nice. Yeah. Yeah, 1 minus that, and then you can d over 2n there. Yeah. So if you picked an element outside Tk, then the set of choices you have shrinks by a lot. So you can't pick too many times from outside Tk because of this. You can pick only up to a certain number of times. And in the remaining times you pick from tk, but by the expander mixing lemma, you can bound the size of tk by something like 2n lambda over d. So if you're picking from tk, then you have only these many choices. If you're picking from outside, you have more choices, but you can't do that many times. And so if you just then count and estimate your things nicely, you get the lemma. That's all there is to the lemma. It's a very simple but clever argument. Okay, so that's it. We take a 15-minute break now, and then we start with some more finite geometry. We introduce some new finite geometries and develop some more theory around them. Okay, so yeah, that's it. Okay, cool. Yeah, and before we start with this new topic, I should really thank Yuval Victorson and Aditya Putukuchi, whose names I have typed in the chat, because they really helped me with the previous part that I presented to you on the Ramsey numbers. And so I just wanted to say thanks to them. And now we move on to the finite geometry. Okay, so the next topic that we discuss is something known as polar spaces. And this is a very, very classical object in geometry, and especially in finite geometry. But it looks like in extremal combinatorics, they're not, I don't know any applications, in fact, so far of polar spaces, except for like a couple of them, which I will share with the KS-free pseudorandom graphs. And I really hope, especially that the extremal combinatorics community learns a bit more about polar spaces, which they can then use in more extremal problems, including Ramsey theoretic problems. So that's my main aim here. So I would go quite slowly. So for the geometry people, I apologize. There'll be some very basic things that I'll describe. And if I make any errors, please correct me in the chat. Okay, so let's begin. We'll take the same approach as before with all the point line geometries that we defined. We have a partial linear space. So a polar space is just, again, a partial linear space. And in case you forgot that was, think of a linear hypergraph, if you know what those are. Okay, so where the vertices will be referred to as points and hyperedges will be referred to as lines. So it's a partial linear space with the following axioms. And the main one is, again, the first axiom, which says that if you take a point X and a line L not passing through X, then one of the two scenarios happen. Either you have a unique line through X which meets L. This is exactly what happened in generalized quadrangles. So either you have this situation, or all of those lines through X, yeah, or all of the, or through every point of X, or every point of L, there's a line joining X and that, which is in your partial linear space. So either exactly one point of L is collinear with X, or all points are collinear with X. And by collinear, I mean there's a line or there's a hyperedge passing through two vertices. So that's the main axiom. And then you have a non-degeneracy axiom, which says that no point is collinear with every other point. So you don't have this trivial sort of a situation that you have a point X, and for any other point in the partial linear space, in this point line geometry, you have a line passing. Okay, that looks bad, but anyway. So you don't have this trivial situation. And that's called non-degeneracy. So let me just write it, because we will see interesting examples where you have a degenerate polar space. Non-degenerate polar space, this one. So if the second condition is not satisfied, then we will call that partial linear space as a degenerate polar space. Okay, that's the main axiom. So not too many things to remember. And what are the examples? So clearly, every generalized quadrangle is a polar space. right? Because you had that axiom, the first one, where it said, yeah, only the first condition can happen, that only exactly one point of L is collinear with X. And then you can get the non-degeneracy of the generalized quadrangle, the second axiom of the generalized quadrangle, from the second axiom here. So every generalized quadrangle is definitely a polar space. So we are now generalizing these generalized quadrangles in these multi-line geometries. And the main examples, the so-called classical polar spaces, they come from something known as totally isotropic points and lines of a projective space with respect to a polarity. And that's a mouthful if you don't know any of these concepts from before. So I will describe precisely what all of these things are, what a polarity is, and what are the totally isotropic points and lines of a polarity. Okay, so here's the definition. So a polarity perp, I'll denote it by perp always, is a bijection between subspaces of some projective space. So say PG of n comma f. We are not restricting to finite fields unless we have to. So this is over all any arbitrary field f. Take any n-dimensional, finite dimensional projective space, then a polarity is just a bijection with the following properties. Firstly, if the dimension of a subspace is k, and here I mean the projective dimension. So let's just write it as p dimension. If this is k, then the dimension of S perp is n minus k minus 1. So all the k dimensional subspaces get mapped to all the n minus k minus 1 dimensional subspaces. And maybe if you looked at the dimension, the vector space dimension, so the vector space dimension is k plus 1, and the vector space dimension here is n minus k. Yeah, then that would make a bit more sense, because the vector space dimension is n plus 1, right? The vector space dimension over which you define this projective space is n plus 1. This is k plus 1, and this is n minus k. If you sum them up, you get the vector space dimension. Okay, so it's sort of like taking the complement, right? So that's the first condition. Yeah, it's very easy to get confused between projective and vector space dimensions. And maybe I'm confusing you more by writing both of them, but yeah, slowly you'll get used to it. Though I know like working researchers who all the time get confused by them as well. So it's not really going to help. What is meant by a subspace? Yeah, so just like a vector space. So when I defined a projective space, I said that the one-dimensional subspace of the underlying vector space are the points, the two-dimensional subspaces are the lines, and so on. So any k plus one-dimensional subspace of the vector space, when you look at it as a collection of points, as a collection of one-dimensional subspaces, then that's a k-dimensional projective space. So a k plus one dimensional vector subspace gives you a k-dimensional projective subspace. Yeah, that's what you have to keep in mind. So it's a bijection from k-dimensional to this, such that the following two things are true. Firstly, if S is contained in T, then S perp contains T. So it's like an incidence reversing bijection. If your subspace S, so say a point of the projective space is inside, let's say, a line, then the perp of that line, or the perp of that point, which will be a hyperplane, in fact, would contain the perp of the line, which will be a codimension 2 subspace. And third, S perp of perp equal to S. So these are the three conditions. And this is a very general algebraic and geometric notion known as polarity. The name comes from actually if you look at the poles of the Earth, so I'll just give a very vague thing. You can see the Earth or the sphere as a projective plane using the great circles of the equator and whatever. And then, so the equator, which is the line, gets mapped to the poles, the north and south pole. So you map this equator to these two things, which are the poles. And this thing is a polarity of whatever this projective plane you get out of a sphere, if you know what I'm talking about. I think at least I've confirmed it with some people who are more familiar with these things. That's the origin story of the name polarity. Okay, yeah. Now, whenever you have a polarity of any projective space, there's a very natural sort of a notion that people defined to study these polarities, which is that of an isotropic subspace. So maybe I'll only define what we need. So totally isotropic. So something known as a totally isotropic subspace, which is just a subspace S such that S is contained inside its perp. Okay, that's it. That's the definition. Just try to remember this. And now whenever you have a polarity, okay, let me just actually give you an example. So the most standard example that anyone would think of, irrespective of what area they are working in, is probably this one. Just map your point, any point of your projective space, A0 to AN, to this hyperplane. So this is a zero projective dimensional subspace, and this is a n-1 dimensional projective subspace. And similarly, you can actually see it from the properties that I'll talk about. You can extend this map to have a bijection between all the other subspaces that we need for the definition of a polarity. Okay, so for any point, you define this hyperplane using this equation, using these coordinates. And remember, it's a one-dimensional subspace in a vector space sense. So, and these are all this is a non-zero vector, so you get a non-trivial equation here. Okay.
Sorry, I'm still confused.
Yeah.
So in this, the polarity is a bijection from the set of subspaces of the projective space to the set of subspaces of the projective space?
Yes.
So what about the entire projective?
Oh, yeah, sorry. So I should say that the empty subspace gets mapped to the entire one. Yeah.
Oh.
Yeah, that's you need that to make things conceptually okay. Yeah, and that's a good point. Yeah. So if you imagine these projective subspaces, the collection of subspaces as a lattice, right? You can imagine these vector subspaces as a lattice. Yeah, if you're talking about vector space dimension, Emilio, then that's the case. Yeah, but that's the confusion. Yeah, so if you have the projective dimension k, then that can map to a n-k-1 thing. So yeah, that's a codimension. Yeah, 1, I guess. Yeah, but that's the idea. Yeah. Okay, so if you imagine the lattice of all the subspaces of a vector space, then you are sort of mapping the lowermost layer of the empty subspace with the topmost, and the first with the second top layer, and so on. So you are reversing these things, reversing this lattice in some sense. That's what's happening with the polarity. Okay, there are some very basic properties that you can prove just from the definition that I gave you, but it's good to have these in mind, and you can prove it yourself. Firstly, if you have any two subspaces, so projective subspaces which correspond to vector subspaces of one higher dimension, you can take their span, S plus T. If you take the perp of that, then this is in fact S perp intersection T perp. And in the other direction, if S intersection T perp is in fact S perp plus T perp. Try to prove it just from the definition I gave you. This sort of tells you that you can actually, from just the action on points of the projective space, you can determine the action on all subspaces. Right? For example, say you have a line, then it's spanned by 2 points. you can just take the perp of the first point and the perp of the second point and take their intersection. That will be the perp of the line. So to define a polarity, all you need is what I've given here. The action, the bijection between the points and the hyperplanes. That's what you need. Okay. Now, another really nice thing is that this is a downward closed family. So if S is totally isotropic and you take any subset, any subspace which is contained in S, then T will also be totally isotropic. That's another thing you can prove just from the definition. Okay. And maybe if you are more comfortable with your perp from the real geometry or the real vector spaces, these things you know, right? Where you have this perp is the orthogonality, let's say the standard dot product. So keep that intuition in mind whenever you're looking at these properties, and that intuition carries over basically for all fields. I'm trying to make an abstract, yeah, so the polarity definition, it's a bijection between subspaces such that a k-dimensional subspace gets mapped to n minus k minus 1. These are the projective dimensions. These are the vector space dimensions. It's incidence reversing. So if S is contained in T, yeah, then S perp T perp, and yeah, it's an inverse of itself. So if you just map S, it goes up in the lattice and then comes back if you apply perp again. Okay, so yeah, it's probably not so easy to maybe remember all of this if you're seeing polarities for the first time, but hopefully by the end of the lecture or by the next lecture, you'll understand, you'll remember all of this. Okay, so the main thing, does a polarity always comes from a bilinear form? Yeah, we are going to get to that. So we will actually tell you, I will tell you what are all the polarities of a projective space. Where do they come from? And in fact, symmetric bilinear forms would be one example, which gives you polarities. Yes, yeah. But there are many, many other examples. That's what makes this whole thing very interesting. You have plenty of things, objects to play around with. Okay, so why am I talking about these isotropic points? And I will probably skip saying totally because I don't care about the other sort of isotropic thing. I just say isotropic. So the totally isotropic points and lines, they always form a polar space, but a possibly degenerate one. So the second axiom of the polar space might not be satisfied, but they will give you a polar space. And let's try to prove this. So the main thing that we have to check is if you have a point X and a line L in the projective space. So remember, we are working over PGN, F. If you have this, then you want to show that either exactly one point of L is collinear with X or all points of L are collinear with X. And for that, I first claim that a point Y, a totally isotropic point Y, is collinear with X. So collinear inside this point line geometry. So we are not just saying collinear in the projective space because any 2 points are collinear. To any 2 points you have a line, it's a linear space. But we are saying we only look at the totally isotropic points and the totally isotropic lines and look at the geometry found by them. Okay, so a point Y is collinear with X if and only if X is in Y perp, or equivalently Y is in X perp. So this thing of perp is actually collinearity, and that will require some thought to really prove this. It's not the most immediate thing. Okay, I leave it to you. Using these basic properties, you should be able to do this. And once you have that, then you sort of immediately see where this one or all property is coming from. Right, now note X perp is a hyperplane. So X perp intersection L is either equal to L or X perp intersection L has cardinality 1. So any line and any hyperplane either meet in exactly one point or the line is completely contained in the hyperplane. These are the only two possibilities. And that's really, so intuitively, that's where the axiom is coming from. Okay, I'm leaving some details here. You have to really check if you want to check all the axioms are properly satisfied, but that's the idea. Now, for the second axiom, for it to be a non-degenerate plane, you need the condition that, so it is non-degenerate if and only if for all x, for all totally isotropic points, x, x perp does not contain all the other, it does contain x anyway, so it does not contain all totally isotropic points. So this x perp, this hyperplane, does not contain all of the totally isotropic points, right? So we have x, we have this hyperplane x perp, which contains x. It also contains a lot of other points, but it should not contain all of the totally isotropic points. There should exist some y such that y is in y perp, so y is totally isotropic and y is not in x perp. So for all x, there must exist some y with this property, and then it will be a non-degenerate polar space. Okay. Now, yeah, so we will see, of course, we will see examples. So this is maybe too abstract so far. We will see plenty of examples, but let's just develop more of the theory, just a little bit more, not much. Okay. Firstly, whenever you have a polar space, you can immediately define the notion of a rank of such a polar space. And yeah, here's a definition. I'll read it, but intuitively, what exactly is happening here? We have this lattice of subspaces of the projective space, right? And we are picking some of the elements from this lattice. We are picking some points, some lines, some solids, whatever. Now, and these are the totally isotropic elements, right? We are picking. Now, the maximum dimension or of this poset, the subposet that we pick, the height of this subposet or the maximum vector space dimension of any totally isotropic subspace is what is known as the rank of a polar space. And you should, yeah, there will be confusion for sure between projective and vector space dimension. You should think of rank as maybe the number of distinct type of objects there are in your geometry. So if you only have totally isotropic points and totally isotropic lines, then you have rank 2. If you also have totally isotropic solids, then you have rank 3. Oh, sorry, planes, then you have rank 3, and also solids, then you have rank 4. That's the idea. Okay, and now you can immediately see that this rank is always at most the dimension of the underlying vector space divided by 2, and the reason is as follows. S is contained in S perp. This implies that the dimension of S is less than equal to the dimension of S perp, and this, let's say the vector space dimension maybe this was equal to n minus k. I guess, yeah. Even I'm confused now. This was yeah. So say S has dimension, vector space dimension, k. Then this will have vector space dimension n minus k, where n is the dimension of V. N plus 1 is n minus 1 is the dimension of the projective space. But anyway, you will get something like k is less than equal to n minus k, from which you get yeah. You should again intuitively see that this as the middle level layer is the most you can contain in this lattice, right? Because anything above it will send its perp to something below the middle level, and then that can't be contained in the perp then, right? Okay, and any non-degenerate rank 2 polar space. So we will give many examples of polar spaces, but in all of them, if you assume your rank is 2, so in those examples, if you only have points and lines, then you can prove it's actually a generalized quadrangle. So this will be up like many examples of generalized quadrangles that you can construct. They come from these polar spaces then. So all the examples you will see, you can take the special case of rank 2 and you get all the generalized quadrangles you want, which that you can play around with and then hopefully improve the bounds on explicit constructions of Ramsey numbers, right? So that's the motivation for all the extremal combinatorics people out here. Finally, this is a very, very nice exercise, and it's there in the exercise sheet, that if you take the collinearity graph of any polar space that has some order. So here, unlike generalized quadrangles, we are not going to prove that just from the axioms you get an order s comma t, that you get that there are constant number of points on each line and constant number of lines from each point. But if you assume they have an order and say you assume they have n points, so you have a polar space of this order and n points, then you can prove that the collinearity graph is actually a strongly regular graph. And maybe to make your life simple, I'll write down the parameters here and then give me a second. So k is s times t plus 1. You will see this soon on your screen. Lambda is k minus 1 minus divided by s, and mu is t plus 1. I hope now you can see it. Yeah. So there are these parameters that you can compute, and it's a very nice exercise. And I'll tell this to all the geometry people who know what these objects are. Don't use the classification of polar spaces. So don't use the fact that every polar space is either a generalized quadrangle or a rank 3 polar space, a rank at least 3 polar space, and then you have a classification of them. Don't use that. So this is a fact that everyone sort of knows in geometry, but proving this just from this axiom is a very nice and fun exercise, which I learned from Ferdinand Edinger. Yeah, you should definitely try that. Okay, so we started with the motivation from Ramsey theory that we will somehow use them to construct nice pseudo-random graphs. But yeah, they also give you a lot of strongly regular graphs. In fact, they also give you a lot of nice groups, like many finite simple groups, many of the infinite families of finite simple groups, they actually come from polar spaces. That's historically that was one of the motivations for studying these objects. All right, and now, as Relinde said in the chat, let's just look at some examples of polar spaces. And the most natural example that you would come up with is through a symmetric bilinear form. And if you don't know what those are from your linear algebra 101 or 102, I don't know when you see these things, then this is just a map from V cross V to the underlying field such that it's linear in both coordinates. Now, any symmetric bilinear form is called non-degenerate if there is no non-zero vector which is orthogonal to every vector. So for every non-zero vector, there exists some other vector such that beta of u comma v is also non-zero. This is the definition of non-degenerate symmetric bilinear forms. And the standard example is the following sum of xi, yi, right? The so-called standard dot product, at least in the real and complex spaces. All right. So whenever you have a symmetric bilinear form, a non-degenerate one, you can define this map. So for any subspace U, any vector subspace U, you can define its perp, the so-called orthogonal complement, I guess, if you take all those vectors for which beta of x comma u is 0 for every u in U. So for everything in U, for every vector in U, yeah, and every vector in whatever this U perp is, if you take anything here, then beta of x comma y will be 0. This is a very common notion of orthogonality, what we like to call orthogonality of two vectors. Okay, and this again, I'm going to leave the proof because yeah, we need to get to the fun stuff of using polar spaces, but it's in the lecture notes, so you can see that. Yeah, I might have like a not so pleasing proof there using matrices and rank nullity theorem. Maybe some purist over here can give a better proof of this, but this is true. Okay. And so this is a very good way of getting polarities, right? Just think of any non-degenerate symmetric bilinear form. You have a polarity, you have a polar space, you have all of these strongly regular graphs if you assume it's finite with some number of points, and you have generalized quadrangles from them. You have all sorts of nice objects by just starting with something as simple as this. Okay. In fact, as I said, so this is just a polarity, right? This is just a polarity. It gives you a polar space, but that polar space might not be non-degenerate. So the second axiom might not be true. For that, you can just assume that the characteristic of your field is not 2. So if it's not binary, characteristic 2, then in fact, you get a non-degenerate polar space. Let's quickly check that. So for every totally isotropic point, we have this picture again, X perp. We want to show that there exists a Y such that Y is totally isotropic. So beta of Y comma Y is 0 and beta of X comma Y is not 0. We want to demonstrate that such a Y exists. So Y is not an X perp. And for that, you can just do the following. Take the line joining them in the projective space. And then on this line, any arbitrary Z can be written as something like X plus lambda Y. Okay. Now you just need to check that there exists some lambda or there exists some Z for which these conditions are true. Okay, so I'm not getting this Y. Either these conditions are true for Y itself. So beta of Y comma Y is 0 and beta of X comma Y is definitely not 0 because Y is not an X perp. So either we already have this. If not, then my claim, and I'll just leave it probably. My claim is that you can pick some other point on this line for which this condition is true. And once you plug that, once you just evaluate beta of Z comma Z, and you get some equation, and you want to make sure that is 0, what you get is lambda equal to something where there is a factor of 2. So that's where you assume your characteristic is not equal to 2. Okay. So for characteristic not equal to 2, this will give you a non-degenerate polar space. And in the exercises, you can see what happens for characteristic 2 as well. You can give interesting examples there. All right. So that's all about the symmetric bilinear forms. That's one way of getting polar spaces. Now, that's not the only way. There are many, many ways of getting polarities and polar spaces. And if you actually want to understand even the symmetric bilinear forms, just characterize what sort of symmetric bilinear forms are there, what sort of different polar spaces you can get by just taking symmetric bilinear forms, what sort of non-isomorphic ones, then it's really a good idea to go to something known as quadratic forms. So even to understand the symmetric bilinear forms, it's a good idea to understand quadratic forms, and I'll define what those are. But moreover, they actually give you some new examples when you have characteristic 2. So in characteristic 2, this was potentially a degenerate polar space, but then you can use something known as a quadratic form and you get non-degenerate polar spaces there. That's the main idea behind them. So here's a quick definition. We have only 10 minutes. I know this is very heavy on all the theory, but yeah, this will hopefully pay off in the end when we start looking at the constructions. Okay. So a quadratic form is just a function from a vector space V to its underlying field, such that whenever you take a scalar multiple of V, then you get lambda squared times Q of V. And if you take this function over here, Q of X plus Y minus QX minus Q of Y, then this function is a symmetric bilinear form. So they're intimately linked with symmetric bilinear forms. And the standard examples that you get is just using coordinates. You pick any degree 2 homogeneous polynomial and use that to define your function. And that will give you a quadratic form. In fact, if you remember the first lecture, you get a hypersurface in PGV. And the conics are a special case. Okay, very classical objects. They don't have anything to do with finite geometry for them, for like the motivation behind them was, I think, number theory when Gauss started studying them. So they're very, very classical, well-studied objects for like more than a century for sure. Yeah. Now, for quadratic forms, just like we did for symmetric bilinear forms, we can define a bunch of points of the projective space and a bunch of lines for the projective space that will together give us a polar space. That will give us this abstract point line geometry, which is very interesting. So here you define a subspace S to be totally singular if all elements of S satisfy Q of U equal to 0. So in terms of, if you're more familiar with this hypersurfaces or the algebraic variety stuff, then these are the subspaces contained inside your hyperspace. So you have this hypersurface. Yeah. You have this hypersurface, this projective variety, let's say, and these are all the subspaces contained in it. Maybe all the points also, but all the lines, even higher dimensions as well, they can be contained. And finally, we call Q to be non-degenerate if for all non-zero U, which are contained in your quadratic or your quadratic subspace, there exists some V which is not orthogonal to U with respect to this beta corresponding to Q. So let me just say, because I'll be saying this anyway, I keep forgetting things. So quadrics are the collection of points, the points in the projective space where Q vanishes. So if you just look at the whole thing, all the points in the projective space where Q vanishes, then that's known as a quadric. So I'll just call that a quadric. It will be a collection of points in the projective space. And a quadratic form is a function on the underlying vector space. Okay, and now here's the nice thing, that if you take all of these totally singular points and lines in a quadratic form, then you always get a non-degenerate polar space. It does not matter if your characteristic is even or odd or 0. It does not matter. You always get a non-degenerate polar space. That's the sort of a beautiful thing about quadratic forms and sort of an ugly thing about the symmetric bilinear forms, even though we are all more comfortable with symmetric bilinear forms because that's the sort of thing we see in our Euclidean geometry and other things, basic linear algebra, right? We see the standard dot product. But this is somehow more, conceptually, this is something better in some way. Yeah. Okay, and I wanted to write down the proof maybe, but we don't have that much time. It's the same idea. So it's the same idea that we saw before. You just want to check the non-degeneracy condition because the fact that it's a polar space follows from the following, that totally singular implies totally isotropic. So this is with respect to the quadratic form, and this is with respect to the underlying or the related bilinear form. And so they do form a possibly degenerate polar space because they are totally isotropic with respect to a symmetric bilinear form, but non-degeneracy then you have to check using this Q. So you have to, it's the same trick that you saw before, and you can do this yourself. Okay, and finally, a very important remark. If the characteristic of your field, of your underlying field, is not 2, then these two objects are equivalent. Then a subspace is totally singular if and only if it's totally isotropic with respect to the bilinear form. So here it was only one direction, but if the characteristic is not 2, then it's true in both directions. So then you don't really gain much. Maybe conceptually you gain something, but they're equivalent objects, the symmetric bilinear forms and quadratic forms, which is the main reason why, for example, in the real space or in the complex space, we rarely talk about these things. Right? We usually just focus on the symmetric bilinear forms. Yeah, characteristic is 0 there, so it's all fine. And that's the main thing that I would like to end with, to actually tell you that these forms can be classified. So the set of all quadratic forms can be classified, depending on what field you are working with. But over finite field, definitely there's a very nice classification. You can classify them over real numbers and complex numbers as well. I'm not sure if there's a classification over arbitrary fields. Maybe there is. I'm not sure. But for most nice fields that you want to work with, you can actually classify all the quadratic forms. You can say exactly what they look like. And this is due to Witt, I think, from, I don't know, maybe Valentina or someone can tell me which year this was in. This is like the classical theory of quadratic forms. Yeah. And instead of giving you a proof of that and developing all that theory and boring you to death with all that algebraic theory which goes in classifying this, I'll just tell you what the classification looks like, so you know what sort of objects you are dealing with, what sort of finite geometry objects you have at your disposal to use in extremal combinatorics or in Ramsey theory, so that you can work with them, prove nice things with them, give new constructions with them. And in fact, in the exercises, I'll give you another nice construction using polar spaces, which has something to do with two-round problems, but then it can be applied to Ramsey problems as well. Okay, so let's just go through this classification very slowly. And then in the next lecture, we will prove some properties of quadratic forms and the polar spaces coming from quadratic forms using this classification. Okay, so say you have a quadratic form over FQ in an n+1 dimensional vector space, and let R be its rank. So R, let's say R is the maximum vector space dimension of a totally singular subspace. Then there are only three possible cases that your n+1 here, the vector space dimension, is exactly twice of the rank R. So it's even and it's exactly twice of R. Or it's odd, then it's 2R plus 1. Or it's even again and it's 2R plus 2. So if you go the other way around, say I give you a vector space of dimension 6, let's say, then there are two possibilities, that you have a rank 3 polar space in it, or a rank 3 quadratic form in it, or a rank 2 quadratic form in it. Right? These are the possibilities for even case, and for odd, the rank has to be exactly whatever the maximum possible thing. Okay. So this sort of tells you that the maximum possible rank that you can have, we saw a bound on the rank, right? In terms of the dimension of the vector space, the maximum possible rank is achieved, basically, except in this case where it could be one lower. Okay, so then one of these things is true, and these three things correspond to the following three cases here, which says that there exists some basis of your vector space. So there exists some change of basis in which you can really write down these quadratic forms in one of the following ways. So the first thing is known as something called hyperbolic, which says that Q is equal to, let's say, x0, x1 plus x2, x3 plus dot, 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 x of n plus 1, n times n plus 1, so 2r minus 1, x of 2r. If I get this wrong, please correct me, but I hope this is okay. Yeah. So this is known as the hyperbolic form. There's some parameter here which will play a role later. We'll see what this is, but either it's this form, and this is the case when n plus 1 is equal to 2r, or it's the parabolic form, which is, which is x0, x1 plus dot, 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 x2r minus 1, x2r, but now the dimension is in fact 2r plus 1, so there's this other variable remaining, and it's actually, if I'm not wrong, it's 2r plus 1 square. And let me check what this mu is. It's going to be, it's hard to remember for me. Yeah, so where this mu is, where this mu is equal to 1, for Q even, and mu is 1 or a non-square for Q odd. And these two really, 1 or non-square, they give you actually different quadratic forms. So these two forms are not really equivalent, but the underlying geometry that we will see end up being equivalent. So in fact, they both give you isomorphic polar spaces. Okay. And finally, there's this other form, which is called the elliptic quadratic. Someone mentioned them in a chat before, where you have x0, x1 plus so on, 2r minus 1 x2r plus some function phi, where phi is inside, of course, the last two variables. So x of 2r plus 1, x of 2r plus 2, and it's irreducible degree 2 and homogeneous. So there is some irreducible degree 2 polynomial at the back. But the common thing is this. So in every quadratic form, you have this first like nice terms, and then in the end, you either have the zero polynomial, you have a polynomial in one variable, or you have a polynomial in two variable, which is irreducible. That's a classification. And we will use this in the next lecture to actually get some hands-on things about the polar spaces, count the number of points, and so on, look at some graphs associated with them. And that's the plan for the next lecture. Okay, so thank you. And if you have any questions, then just let me know. Yeah. Thanks.